So when we're drawing the electric field, we draw it as if it's lines coming out of whatever it is that's causing it. So wherever there's a charge, it will have an electric field around it, and we can represent that with these things we call field lines. The first thing we're going to look at is a point charge, and we're going to pick a negative point charge. The reason for that is because electrons are the most common things that cause us to have an observation of electric field. So imagine an electron. It pulls in, it has an electric field around it which we can interact with that works in this sort of spherical way that you can see in front of you. Now, the field lines are sort of an imaginary thing. They are there. There is something there. There aren't necessarily these lines, but that's our way of representing it, representing how it affects things. So we first need to think, how would a charge behave in here? And when we come to the convention of drawing arrows on our field lines, it is how would a positive charge behave in a field. So all of these, if I put a positive charge in here, it will be drawn in because opposites attract. So we're going to put all of our lines with an arrow pointing in to the theoretical centre of our charge. Now we've got to be careful now, just like with gravitational fields, not to draw our lines penetrating the body of the charge or penetrating the body of the electron or charged sphere or whatever it is. The behaviour of the electric field isn't necessarily the same inside there. Now if it's an electron, it isn't even really a particle to speak of anyway, so that's a really very small point. But it would still apply if it was a huge sphere, let's say the size of my head. It would still apply, it would still look the same. Now, there are a couple of things that are worth mentioning, and that is, we can see that even though they seem uniformly spaced on a radial way, they are in fact not uniformly spaced, linearly escaping. So, if I draw a fixed size circle, there and there, I am intersecting a lot more field lines here than I am there. Think about what that might indicate at this stage. Just going to say this, even though it's probably pretty obvious. If it was a positive charge, the field looks absolutely identical in terms of its shape, but what we will find is that the arrows that we draw on it should be facing in the opposite direction, because if I put a positive charge within it, it would experience a force of repulsion, and those arrows need to show what direction that's going in. Now, it is possible to create charge on plates. Now, we do this for loads of reasons. We do it in capacitors, we do it in batteries, and the behaviour of the electric field in those settings is important to know. It is a uniform electric field between two plates, which means that if I have a plate of a fixed length, and I put another one underneath it of the same fixed length, between them, if they've got a constant separation, you will get a constant electric field strength, and that will mean that the field will have the same spacing, or we will draw it with the same spacing anyway, all the way along its length. We still stick to the convention of the direction of the field, and that is, what would a positive charge do? It would be drawn to the negative and repelled from the positive. So this would look like downward arrows. And we should see this equal spacing between each of these lines if this was looking exactly the same. I know it's a little bit messy, the gaps are not exactly the same as they're supposed to be, right? You should always be drawing your lines in an exam, and always with rulers. I, at this point, am not, which is bad practice, I suppose. I'm sorry about that. So now we're going to look at this property, electric field strength. And before we look at that equation at all, we're just going to look at how the field lines themselves tell us what the electric field strength is. So the first thing we're going to look at is that thing I asked you to think about earlier, and that's if I draw a fixed size circle, let's say here, or I'll do it as an oval, there, and I draw it right over here, similar size, then what we can see is that this one is cutting or intersecting a lot more field lines than this one. And that is telling us something. That is telling us that there is a higher field strength in that area than there is in that area, right? And that seems obvious. The closer we get to a thing, the more we experience a force from it. Other than certain weird things like the strong nuclear force, that's pretty constant in terms of our interaction with forces. You get closer, it gets you harder. This is a spherical charge, or a spherical electric field. If we look at a uniform field, however, no matter where we are within the field, even if we get closer to the plates, if I draw a fixed size anything within there, I'm intersecting with the same number of field lines. So the field itself is constant within those plates. Regardless of how close you get to the positive plate or the negative plate, the field should be exactly the same. Hence the term uniform electric field. Right? Spherical electric field gets stronger as you get closer or weaker as you get further away. Uniform electric field, constant field strength, indicated by the spacings of the field lines. So density of the field lines, how well packed they are, tells us how strong the field's going to be. So now we're going to use the electric field strength equation, which is electric field strength E is equal to the force acting per unit charge. So E equals F over Q. Now what that means is that if I put a charge here, let's say it's a positive charge, and it experiences a force of 10 newtons, and it has a charge of, let's say, 1 coulomb. These are ridiculous things, by the way. This is not common at all to experience these numbers. They're normally really, really small, but I'm just doing it for the ease of it. So if I experience a force of 10 newtons on a charge of 1 coulomb, that means the electric field strength at that very point is equal to the force of 10 newtons over a charge of 1 coulomb, which will give me an electric field strength of 10 newtons per coulomb. Does that make sense? I should hope so. There are some questions now to try out which are going to test what I've just told you. I would like to say taught you, but I think that applies later on. So what I've just told you, there'll be questions on underneath.